Howdy, I'm Clinton Crowley, a geologist and a grad student at the University of Texas at Dallas. And I want to tell you more about the continental crust of our nation, the United States of America. This is the second of a three-part series about the continental crust the U.S. is built on and the sedimentary basins that lie on top of it. The crust and sedimentary basins contain critical mineral and energy resources. We can safely dispose of many toxic wastes and rocks far beneath the surface. Crustal rocks of the continental U.S. will be increasingly important in the transition to sustainable energy. In the first video, we saw how geophysics tells us that U.S. continental crust is around 30 to 50 kilometers thick, and something about its composition. Now let's look at the geologic evidence, the rocks of the U.S. crust themselves, not just their seismic signatures. In much of the U.S., the crust is deeply buried beneath younger sedimentary rocks, for example, in most of the Midwest and Great Plains and the coastal plains. But in a few places, mostly in the eastern and western mountains, the crust emerges onto the surface. Most of these are igneous and metamorphic rocks that aren't just millions of years old, they're billions of years old. The whole U.S. is underlain by igneous and metamorphic rocks of the crust. Geoscientists study both crust and sedimentary basins using different techniques. We have learned that the crust is a patchwork quilt of regions made by different events at different times. These regions are called Crustal Provinces. The events that formed the Crustal Provinces happened so long ago that there is often no evidence on the surface today of the once great mountains, rifts, and volcanic fields that formed them. Radiometric dating allows geologists to know when different crustal provinces formed. The oldest U.S. rocks formed in the Archean eon, over 2,500 million years ago. The oldest rocks in the U.S. are found in Wyoming, Minnesota, and the Upper Peninsula of Michigan. These are all over 3,500 million years in age. Most U.S. crust formed in the Proterozoic eon between 2,500 million years ago and the beginning of the Cambrian period approximately 541 million years ago. How does radiometric dating work? It works because we know the rate at which radioactive elements like uranium decay to stable elements like lead. This is a totally different process from tooth decay, moral decay, and rotting organic matter. Igneous rocks like granite form as molten rock, that is, magma cools and solidifies. The elements in these cooling magmas sort themselves into different minerals. As some of these minerals form, minerals like zircon, they trap atoms of radioactive elements within them. How does that happen? Isn't zircon only made from zirconium, silicon, and oxygen? Zircon is a mineral that's like an exclusive, snobbish social club. You have to be invited, and the Zircon Club chooses its members based on the size and electrical charge of atoms. To join, an atom must be the right size and have the right number of electrons to fit within the zircon's crystal framework as the mineral grows in the cooling magma. Uranium is just the right size to fit in the framework of the zircon crystal, and it has the right charge to be welcomed into the Zircon Club. Atoms that are the wrong size, or whose electrical charge isn't acceptable in the Zircon Club, go elsewhere and join other mineral clubs. Lead has the wrong size and charge, so lead is absolutely not allowed to enter the doors of Club Zircon. But lead is found in zircon. How can that be? When a zircon crystal is brand new, its ratio of lead to uranium is 0. But this ratio grows with time because uranium decays to lead at a known rate. That lead forms inside the zircon crystal and is trapped in it. The ratio of lead to uranium in the zircon reflects the amount of time that has elapsed since the zircon that contained it formed. That is also the age of the igneous rock the zircon formed in. There are many other radiometric dating techniques using other minerals that contain radioactive elements, but the underlying principles are basically the same. So, what good is it knowing how old some rock is? Radiometric dating allows zircon and other crystals to tell us the history of the birth and evolution of the crustal provinces that make the U.S. continental crust. A single age doesn't tell us much, but the big picture, with many ages plotted on a map, allows us to distinguish regions where the crust has approximately the same age. This is a crustal province. The age of the rocks, more than the rock type, is how the U.S. crust is divided into crustal provinces. Here's a simplified map of U.S. crustal provinces, and it's a very different map of the U.S. than any you may have seen before. There are 7 major U.S. crustal provinces that range from 3,500 million years to less than 100 million years in age. Let's consider each of them from oldest to youngest. The oldest crustal province in the U.S. dates from the Archean eon, older than 2,500 million years in age. This is the southern extension of a much larger tract of Archean crust in Canada called the Laurentian Shield. This Archean crust is the core of baby North America and gives it its name, Laurentia. 3 crustal provinces were formed in the 3 subdivisions of the Proterozoic eon, which encompass the next 2 billion years of Earth history. The Paleoproterozoic era lasted for almost 1 billion years and was the first and by far the longest of the 3 Proterozoic eras. A lot of U.S. crust formed in the Paleoproterozoic era. Examples of these rocks are preserved in the Rocky Mountains of Colorado, New Mexico, the inner gorge of the Grand Canyon in Arizona, and lie buried beneath the northern Great Plains. More U.S. crust formed in the Mesoproterozoic era between 1,600 and 1,000 million years ago. In the early Mesoproterozoic, a lot of U.S. crust formed south of the Paleoproterozoic crustal province, from Big Bend in Texas all the way to New York State. Most of this crust is buried, but some lies exposed in Texas' Llano Uplift, Missouri's San Francois Mountains, and New York's Adirondacks. The whole mid-continent region now had a foundation, but crust of the eastern and western U.S. did not yet exist. Montana, Idaho, Nevada, and Southern California were on Laurentia's western seaboard. Rocks that formed on the coast of that ancient ocean are visible today in Montana's Glacier National Park. In the late Mesoproterozoic era, between 1,300 and 1,000 million years ago, more new crust was added to the eastern side of Laurentia. This is a belt of deformed rocks called the Grenville Orogen, named for the place in Canada it was first identified. This Grenville Orogen is where a great mountain belt rose in a continental collision that formed an ancient supercontinent called Rodinia. The Grenville Orogen has long since been worn down, but you can see and touch the roots of Rodinia in the Great Smoky Mountains of Tennessee and North Carolina, and in the Adirondacks of New York. Halfway through the Grenville mountain building event, a volcanic rift began to tear apart the middle of Laurentia. Rifts are like planetary stretch marks they form where the crust is being pulled in opposite directions. Floods of basalt lava filled a huge cleft in the crust from Kansas to Minnesota and eastward to Michigan. It was like today's East African Rift and is called the Mid-Continent Rift. Continental stretching stopped after only a few million years, but the great scar remains. You can touch it in Michigan's Keweenaw Peninsula. Crust under the U.S. East Coast formed in the Neoproterozoic era, which lasted from 1,000 to 541 million years ago. The big event during this time was the breakup of Rodinia. Evidence of this supercontinent's disintegration can be seen deep in Arizona's Grand Canyon, in Utah's Uinta Mountains, and in Virginia's Catoctin Greenstones. More rifting near the edges of Laurentia occurred at the dawn of the Paleozoic era 541 million years ago. Evidence of this rifting can be seen in igneous rocks that outcrop in Oklahoma's Wichita Mountains and Arbuckle Mountains. This rifting episode took a slice of southeastern Laurentia and gave it to Argentina. Argentina is still using it. We have a pretty good idea of what Paleozoic Earth looked like. There were two supercontinents, Gondwana in the south and Laurussia in the north. Gondwana consisted of South America, Antarctica, Africa, Australia, and India. Laurussia consisted of Laurentia, parts of Europe, Central Asia, and northern China. These two supercontinents collided about 300 million years ago to make everybody's favorite supercontinent, Pangaea. Some of the greatly eroded, folded mountains created by this collision can still be seen, from the Appalachian Mountains of the eastern U.S. to the Ouachita Mountains of Oklahoma and Arkansas, all the way out to West Texas' Marathon Uplift. Soon after the collision that made Pangaea in the Mesozoic era, the west coast became an active, convergent plate margin and has been one ever since. Millions of years of magmatism along this plate boundary formed the Mesozoic Crustal Province that lies beneath the Pacific Coast states. Yosemite National Park in California reveals some of the huge mass of granitic rocks called the Sierra Nevada batholith. North America took on its modern look when Pangaea broke up about 200 million years ago. North America got an unexpected gift when the Atlantic Ocean and the Gulf of Mexico opened. Some crust that once belonged to Gondwana was left behind, and now lies under Florida and neighboring southeastern states. In the most recent 66 million years, the Cenozoic era, a little bit of crust was added to North America and Washington's Olympic Peninsula. Here in the Pacific Northwest, the continental crust is still growing. Cenozoic arc magmatism on this plate boundary built the spectacular Cascade Range. Its volcanic peaks tower over Washington State, Oregon, and Northern California. Let's review the story of how the crust of the continental United States slowly formed over 3.5 billion years. The oldest crustal province in the continental U.S. is Archean in age, which forms 15% of it. Next oldest and greatest in extent is the Paleoproterozoic crustal province. It underlies 36% of the continental U.S. The Mesoproterozoic crustal province is the foundation of 24% of the continental U.S. The Neoproterozoic crustal province forms 14%. The Paleozoic crustal province forms 21%. The Mesozoic crustal province forms 8%. The Cenozoic crustal province forms 2% of continental U.S. crust. From now on, it's sedimentary rocks that are the big story in the geology of the U.S. crust. And that's the next video in our series, Sedimentary Basins of the United States. Thanks for watching, and please like and subscribe to the UT Dallas Geoscience Studio YouTube channel for more Earth and space science videos.